Oh no, I think I had it opposite. I keep thinking as R is reflected. I keep thinking as R is reflected. I don't know why. So if R is 0, it's the opposite. That means the velocity in the right medium is 0. That means all of the wave is reflected. Okay, yeah. So that would be a surface that's very good reflecting, maybe a mirror in the house. You put a coating in the back, so all the energy reflects and you can see a good reflection of yourself. You see, so that would be a plane mirror. Right? R is 1 would be if the two mediums are the same density. Right? If R is 1, that means this equals this, the two velocities are the same, and it just means the transmission complete. Right? So all the wave transmits. And then R is 2 would be, so if finally for R is greater than 1, the stress produced in the right medium is magnified. Okay? So then you can have R is half, R is 1.5. So you could have R is half, which would mean there's more reflection than transmission. Right? So we could say if R is less than 1, greater than 0, right? That would be more of the wave's energy is reflected, right? Is that right? Yeah, more of the wave's energy is reflected. More reflection than transmission. If R is greater than 1, more transmission. Usually what will happen in the case of like waves in strings, if the medium here is lighter, more energy will transmit. If it's heavier, more energy will reflect. When the energy comes upon an interface and it says, oh no, I have a difficult route ahead of me, right? So if it is a thick string, it says, I don't want to go there, I'd rather bounce back, you see. Same thing that could happen with a light wave. If a light wave comes and sees, oh my gosh, it's a thick wood, I'm not going to go through the wood, so more of it will reflect from the wood.
So when R is 1, like all waves translate. When R is 1, but why when R is greater than 1? I mean, like it magnifies all the waves when R is greater than 1 instead of like.
R is greater than 1, more transmission, but there's still some reflection.
But there's still.
Yeah, more reflection. What would R have to be so that there is no there's no
reflection, right? So it should be
R should be infinity.
Infinity.
So that there's no reflection at all.
Even though like when R is 1, there's still reflection, right?
Well, let's see. R is 1. All the let's see here.
It says that when R is 1, is the entire wave is transmitted with no reflections.
I kind of like confused because like, when R is infinity,
let's go. R is 1. That means the two mediums are the same.
If R is greater than 1, wouldn't that mean that the left medium is smaller than the right, or less?
Yeah, the density is smaller.
Yeah.
So. So you're saying all the way transmits no reflection.
That's right.
yeah.
R is greater than 1.
Says that it's magnified.
Yeah.
You see here the red one? The blue one is the R is 1. When R is greater than 1, they're showing R is 2. This is a computer simulation of R is 2.
Yeah.
Let's see here.
Now.
See that the transmitted wave has more amplitude.
Yeah, more.
But the reflected wave is smaller.
I understand that.
So that means there is a reflection.
There is reflection.
So there is only no reflection when R is equal to 1.
Yes, when R is 1, no reflection. When R is less than 1, greater than 0, more reflection than transmission. And then here, more transmission than reflection.
Alright, nice.
Okay? This is also true when you are taking quantum mechanics. Physics 4, who's in Physics 4? So when an electron comes with a certain energy, or it doesn't have to be electron, any subatomic particle, and there's a potential well, right? What happens? Let's say infinite potential well that goes on forever, some energy barrier. Part of the energy of the electron reflects, part of the energy of the electron transmits into the barrier. And when it transmits, it dissipates exponentially. Right? If the barrier is a finite barrier, what's going to happen? There's a chance for the electron to quantum tunnel through the barrier. So this is an interface. That's why this topic is such a broad topic, because you can apply it to light waves hitting a mirror, subatomic particles meeting a potential well. You see? So you say, well, what if the electron has more energy than the barrier? Well, then it just goes, transmits, and then comes out. When it transmits, it has a larger wavelength during the time of the barrier, because its energy is less, right? So it comes, meets the barrier, has a larger wavelength. Then once that barrier is done, it goes back to the energy that it had there. But then if you go like this, then it goes through with dissipation, and it comes out at the other end with larger wavelength, because it's less energy. You see? But part of the electron goes like that. So the electron might have a certain chance of being found here, and there's a slight chance of the electron being found there. So where's the electron? You don't know not until you look. It's Heisenberg's uncertainty principle. You don't know where the electron is unless you look. But there's a chance that it's there, and there's a chance that it has quantum tunnel. You see? So that's how our universe began. Before the Big Bang, we don't know what state the universe is in. And there was a huge potential for it to be created, right? So then the fact that we see ourselves in the universe is that our universe was one that quantum tunneled from the previous state that it was in to the present state that it's in, right? It quantum tunneled. So what was the previous state it was in? We don't know. It might have been in the previous state, might have been expanding and then collapsed, and then it met the potential well, and then something happened and blew up again. So then it quantum tunneled to the present state. Or the previous state might have been two other universes that came and crashed into each other, right? And then from that crash, our universe was born. So we don't know whatever state it was in that led to the Big Bang. So in this quantum tunneling state, coming out of the quantum tunneling is like the equivalent of the Big Bang happening. You see? Nice, nice. Okay, so let's do an example there then. There's other websites you can look up if you're really interested in this. Just Google reflection and transmission of waves, as I did here. And a lot of websites will come up. See? Complicated math. Rutgers University. Again, mostly linear algebra. As I always tell you guys, that's the most important class. See the mediums, propagation matrix. There it is. reflection coefficient, linear algebra, differentials, matching matrices, Hermitian operators. Then it just keeps going on and on. Single dielectric slab, reflection and transmission. I'm just wetting your juices here. Right? It's like showing you pictures of cake and you're like, now I can't wait to eat them. Time domain reflection response. Two dielectric slabs. Reflection by a moving boundary. And then problems, possible problems. Multi-layer structures. It's probably a certain chapter from a book. We'll look back at that later. Okay, so now let's do an example that would kind of utilize that. You can say a wave exists in a string and has the equation string of tension 15 newtons. Oh, I just remembered, I forgot an important topic to cover. Change of phase upon a boundary, right? What happens when a light wave meets a boundary that is denser than it? What happens to its phase? Have you covered that in Physics 4?
Yes.
Thin film interference, right?
That's right.
Yeah. Same thing happens to waves in a string. So that would be the topic of phase change upon reflection and transmission. See these ones? Let's specifically focus on for string waves. Oh, I think they're doing light here. Light gets predominantly the more focus when it comes to waves. Yeah, they're still talking about light waves. So string waves get the bad rap. Wave on a string, okay. Yeah, there's a little bit of a simulation there. See, a wave on a string. So a similar thing will be true, of course, for light waves. But I want to kind of focus on the string wave. And also true for sound waves too. So a wave on a string experiences a 180-degree phase shift when it reflects from a point where the string is fixed. So if the string is fixed, you see how it's coming like this, then it bounces back. So essentially the top one illustrating a case where the string is fixed. So I think the book shows something like this. A string is coming, and a fixed example would be if it just hits a wall as a barrier, then reflects back. So if it's coming like this, then upon reflection, it goes like this. The peak becomes a trough. So this is a fixed boundary, or we can call it fixed interface. You see how it's, yes, that top one is the fixed one, where it goes like this, then it comes back, goes back like that. And then this one, you see here, the peak becomes a trough. Peak, then trough. Peak, then trough. They're showing you standing waves also at the same time. The wave is going, coming back, going, coming back. And each time that it's going, coming back, it's experiencing the phase shift, right? And then it's creating a standing wave. Now this one, the middle one, is a moving boundary. So a moving boundary is illustrated like this, and then maybe a ring, and then a pole. This is a moving boundary. Right, so it goes like this, and because this ring can move, the reflected wave comes back the same way. Peak stays as a peak. Right? Like that. Right? Yeah, this is the one that I'm talking about. This is more similar. See here, incident wave. This is fixed end reflection. So incident with pulse comes, goes back with the 180-degree phase shift, right? So this is pi radians phase shift. This one is no phase shift. And it really depends on it's a merely expression of Newton's third law of action-reaction, right? So you kind of read up on it a little bit more, but it has to do with that. So now, the next one, free end reflection, you see? So then you have, this end is free to move, then this one is gonna go, and then it's not gonna have any phase shift. So zero phase shift. Okay. Then the next one is gonna be when you get okay, see the incident pulse and the reflected pulse. That's interesting. They're illustrating this with this. See, it came back with no phase shift. The other one, where was the other one? That's more computer animation. I guess it was, he was holding that end with his hand. So to mimic the wall, he held that and then went like this. And then when it came, then it inverted. So he held it in his, with his hand. Then transmission across boundary. See, this one is more similar to what we're doing exactly. See, less dense, more dense. So a portion of the energy carried by the incident pulse is reflected and returns. The disturbance that returns to the left after bouncing off the boundary is known as the reflected pulse. A portion of the energy carried by the incident pulse is transmitted into the thick rope. You see? The reflected pulse will be found to be inverted in situations such as this. Right? Why is the reflected pulse going to be inverted? Because this medium is denser. You see? So the reflected wave here is going to be inverted. Just like light wave in thin film interference, a light wave in air that comes to, let's say, soap, water, a light wave that comes and reflects pi radians phase shift. Because this one has an index of refraction greater than 1. N is 1.33, and this is 1, N is 1. It's kind of like the light string and the heavy string, right? Why? Because the N value, the index of refraction, determines how fast the speed of light goes, right? The greater the N, the speed of light is what? Slower or faster? You have your test today. The greater the index of refraction?
Slower.
Okay, you weren't sure? Come on, I want your physics 4 test is today. I know you're physics 4. It's slower, right?
So NO over NR is equal to BR
over the speed of light.
Yeah, right.
Right?
Oh, okay, yeah.
Well, same thing with the mass density of the rope. What's the velocity square root of tension over mu? The greater the mass, the less the velocity of the wave in the rope, right? So the mu acts like the index of refraction of the medium. See? So this one, pi radians. Now when it goes here, transmits, the transmitted wave never has phase shift. Then it reflects. Over here, is there a phase shift? If it reflects from water to, well, then it depends what medium the bottom one is, right? If it's glass, then there's going to be another phase shift there. because glass is denser than air water, right? Its index of refraction is 1.52. So you're going to have that thin film interference. Well, we could create a thin film interference here. We can have a less dense, more dense, and then another dense, you see? Then the wave bouncing from here will have 180 degree phase shift, and the wave bouncing from there will have 180 degree phase shift. And then when the two interact here, you can kind of create a simulated thin film interference. All right? So, very, very similar. Now, to understand why the phase shift occurs, they say during the interaction between the two media at the boundary, the first particle of the more dense medium overpowers the smaller mass of the last particle of the less dense medium. You get the idea? So if we can understand this, then you'll understand why light does that. I think this one is easier to understand because you can visualize the string. With light, you're not really visualizing what does that mean, you know. So this causes an upward displaced pulse to become a downward displaced pulse. So you see, imagine the wave is coming like this. That element is moving downward, right? But then this guy says, no, I'm not going to let you move downward. It's going to exert the opposite force. It's almost like something going down against the wall, and then the wall exerts the opposite force, which flips it. You see? So then instead of moving down, so now this one is now on the verge, is now moving up, right? If it's going like this element here, the one down here, imagine you focus on one element of the wave right here, you see? It was moving down. When it met that wall, the wall reversed the direction of this so that it's moving up now. You see? So instead of moving down, now it's moving up. Well, because it met something that's heavier than it. Wow, really deep. You see? The more dense medium, on the other hand, was at rest prior to the interaction. The first particle of this medium receives an upward pull when the incident pulse reaches the boundary. Since the more dense medium was originally at rest, an upward pull can do nothing but cause an upward displacement. So that means if there's two mediums, this is lighter and then this is denser. Right? So this one is pulling down. This guy says, no, you're not gonna go down, you're gonna go up. So then reverses the beam, right? So that this now is going up, but then this one going down, this thing only can do is go down. So that means the transmitted wave is just going down, so that means it just continues going through. Right? So the transmitted wave has no a phase shift. See? For this reason, the transmitted pulse is not inverted. You see? In fact, transmitted pulses can never be inverted, it says. Since the particles in this medium are originally at rest, any change in their state of motion would be in the same direction as the displacement of the particles. So that's why if you have a transmitted wave here from light, from air to water, no phase shift for thin film interference. Only the reflection you have to look on which medium is denser. You see? Hopefully that will help you understand two chapters at once. See the before and after snapshots. Less dense. Okay, you see here. Now the other thing you notice from this is that the wavelength here is different than the wavelength there. You see, it's changing.